Okay, so now let's try to implement them into a scheme. So let's go back and I'll take our finite difference and copy it over here and make it solving a second order equation. All right. So again, we have u left, ur, and now let's try to compute our second order derivative. D square u dx square is going to be following this scheme. It's going to be ul minus 2 times u plus ur and divided by delta x squared. Agree? Okay, and now instead of a, I have a kappa. Let's just say it is equal to 1, and du dx is kappa times d square u dx square. Okay, and it's not called advection. Let me call it diffusion. So this is it can be called the heat equation or the diffusion equation because it's also a good model for the diffusion of, let's say, molecular content. So if you have a again, if you have a liquid and you have different concentration of certain molecules in the water, let's say salt. Okay, this is also the equation to describe how does the concentration of the salt gets becoming more and more uniform over time. So it can be called the heat equation or diffusion equation. Du dt is equal to diffusion. That's it. So let's try to start from the same initial condition and see how the solution evolves. I think, what is my t? Wait. X, u, and let's see. Might be too much. Okay, so my initial condition is like that. So let's see, after 100 steps, right? Let's just track the evolution. So this is the initial condition. Let's hold on and see after 100 steps. My solution, we can see it's diffused out in the sense that the sharp corners gets the sharp increase gets smoothed out, right? And let's look at 200 steps. You see the solution is even smoother, right? So see 1,000 steps, and we get the solution gets diffused into a sine wave. And if I track the 10,000 step, then even the large scale variation gets more and more uniform, right? And I think we were looking at when we were just plotting the end of the solution, we see that it's basically a constant. Can even distinguish, right, the solution from a constant. So that's basically the evolution of this the diffusion equation. And of course, we can combine these two equations. And one thing interesting you are going to see later is when I combine these two equations, the scheme I want to use becomes a little bit different. So, for example, here, if I use kappa equal to 0.01 or 0.01, and I have a first order derivative, and I approximate the first order derivative by this previously very oscillatory central difference scheme. Okay, so this scheme, remember, we get huge oscillations, right, when we just without kappa. But now if I have minus a times du dx and plus the second order derivative term, and now we run it, Oh, we didn't set a. Set a equal to 1. Okay. The central difference is also nice in the sense that it doesn't matter what the sign of a is. I can solve it. Let's close this. Oh wait, I think I already plotted the solution. Let me just run it again. Right now, this is the solution. The solution has advanced for one period, and now I'm here with a diffused, slightly diffused out solution. And if you want to track the evolution, right, let's again plot the solution at initial condition like this. At 100, at 10 step, it doesn't really move anything. Let me do it again and hold on so that we can look at the evolution. At the 100 step, we see the solution starting to get diffused and move towards the right. Right. At 200 steps, further move towards the right and diffused even more. Right. And let's look at 400 and move towards the right even more and diffused even more. And if we look at 800, now it's the green line that's moved almost over half of the domain and diffused even more. So at the end, let's look at 1600. Now it's the blue line, right? Gets amplitude is decreased, and at the very end, it's the I think this brown line over here. So this is how we call advection diffusion equation with both the first order derivative and the second order derivative looks like. And next lecture, let's do a little bit of stability analysis to this combined equation, which has a different nature, right, than the either pure advection equation or pure diffusion equation. All right. Again, there is no lecture on Wednesday, and based on your poll, I think only 6 people responded. But like based on what you gave to me and what my availability is, it looks like Thursday late morning, something from 10:30 to 12 looks like a good time. I mean, no. If
start after 11.
Start after 11 is better. Okay. So 11 to 12:30. Okay. So no. Okay. All right. I'll record the video anyway. So let's just say it's Thursday, not this Thursday, but probably the next one, right? From 11 to 12:30. All right.